Warwick. The first one is Tim Sullivan, and he's speaking about stochastic and statistical models at the interface of the modern industry and
that's the workshop. I thought I'd summarize everything all in one go. Thank you very much, Florian, and thanks for the invitation to speak. I should begin, of course, by checking that this thing works. Okay. So I should begin by acknowledging that there are many collaborators on this project and the various applications, many of them from my former life as a postdoc at Caltech, and from very nice interactions with Los Alamos and NIST and other people, including Florian himself. And I'll begin by giving a bit of an introduction to what I want to talk about, the uncertainty quantification methods I want to talk about. And I should preface it all by saying I am under no illusions that any of this is real-time UQ. This is very much sort of design mode viewpoint on UQ. I'll outline the UQ framework that we have developed and illustrate the key theoretical properties and also, time permitting, a few applications. I'm not sure I'll get through all of them. And then give some thoughts about future directions and what I think advances in scientific computing will yield for UQ over the coming years, gazing into the crystal ball a bit. So introduction-wise, I very much see uncertainty quantification as this sort of intersection area where we have mathematics and statistics on one side, a hefty dose of computation, and by applied sciences, I mean that very broadly, in that I'll include, finance and certain things that aren't physical sciences coming in from this side. And stealing a phrase from this 2009 report from the DOE in the States, I think of UQ really as the end-to-end study of the reliability of scientific inferences. So I really see it as quantitative relationships between pieces of information. And ideally, those relationships should be as sharp or, in some sense, optimal as possible. And somehow the duality of optimality is robustness. And these two come together in the same package. And so the prototypical problem I have in mind is very similar to Briggs's talk a couple of talks ago, that I take maybe a certification viewpoint on uncertainty quantification, that I have some system of interest and things denoted with a 0 on them are always the system in reality, not necessarily my model or preferred model or one of any models for it, but reality that I actually want to make a statement about. Reality is picking up some inputs, dumping out some outputs, and the inputs are distributed according to some probability measure, mu0, and there's some outcome that I consider failure of quality control, getting to Manchester too late. And I would like to know the probability of that undesirable event. And on some level, that's just an integral to be evaluated. Whether you could do it analytically or by some sampling technique, it's quote-unquote just an integral. But of course, one of the big problems about the real world, or sorry, I should just say reality, is that you don't know reality's response function G0, and you don't know reality's probability distribution exactly. You may have some idea about them, but you don't know them exactly. So taking a slightly more general viewpoint, I could be interested in the expected value of any quantity of interest under the integral sign here. Could be interested in the probability of some event, in which case my quantity of interest function Q is just an indicator, or I could care about some mean outcome, a variance about some nominal output value, what have you. And the key point is I'm interested in understanding this thing, which I can't really know because it's got reality's zeros on it, when I don't know G0 or mu0 perfectly. So I've got what I would call, in fancy terms, epistemic uncertainty about these key ingredients in my desired object to know. And so one way of posing this uncertainty quantification problem is to formulate it as an optimization problem. So you write down this horribly large set, A for admissible, which is all the things G mu without zeros on them this time, that could be reality according to whatever information you have to hand. So that could be perhaps you've got some archive of data that you can draw upon. Maybe you have some pretty good models that you believe are accurate up to some degree. You've observed some moments of the probability distribution, but you're unwilling to commit to anything more than the moments you've seen. You have some theory, some expert judgment. And what we're saying is we're just going to view this as a feasible set. All we know about reality is that it's some element of this feasible set, but we have no idea which little g, little mu in A is actually realities. Okay? And we're deliberately putting ourselves in a situation where we're not going to say that any one of these scenarios is more or less likely to be reality than any other. So we're taking perhaps a very high consequence viewpoint on this this UQ problem, and adopting a posture of what I would call healthy conservatism, in that we want to know what's the best and the worst that can happen over this class A, but no worse than that. Not to be paranoid, but merely to find out what's going on over this class A. And actually formulating this set is a step that mathematicians themselves cannot do. So this is where the domain experts in whatever application you're looking at, you really, as a mathematician, you really have to have a dialogue with them to formulate this at A, because a mathematician cannot tell you that one of the assumptions you are making is wrong. Okay, that's the domain expert's input. So once you do have a feasible set to work with, the mathematicians like myself can get to work, because the best bounds, the optimal bounds, the sharpest bounds you can give on your quantity of interest now are just found by maximizing and minimizing this functional of the dummy variables, or the dummy function g, and the dummy probability measure mu. You minimize for the greatest lower bound and maximize for the least upper bound over that class. And that is ipso facto the sharpest inequality that you can give on your output quantity of interest, given the information that you've written down in A. If you want a narrower inequality than that, you must specify more information. And in some sense, this is all dressing up in some fancy calligraphic letters, the whole idea of generalized Chebyshev inequalities, which, that's just one of many references on that. But what I like is that historically it's also faithful to the origins of probability theory. George Boole, in the middle of the 19th century, didn't think of probability of an event as one number. He thought in terms of what we would now call interval-valued probability. So it's actually quite historically faithful. And if you're interpreting these probability distributions as a subjectivist, as say a prior belief, then this is the robust Bayesian point of view, that you haven't committed to a single prior. You're interested in a class of priors and hence a class of posterior predictions. And to make these optimization problems actually computable, actually tractable, there's a very strong analogy you can draw on between this situation and the situation of linear programming. So if I ask you to extremize a linear functional over this polytope, you would sit down and think for a few minutes and realize that the extreme value must be found at one of the extreme points of the polytope. And something very similar is true for these uncertainty quantification optimization problems, that you basically go to the extreme points of this set of scenarios A. And what do these extremal scenarios look like, and why are they so nice to compute with? Well, the heuristic, before I blind you with the theorem, is basically if you've got n pieces of information about some random variable, you get to pretend that that random variable takes at most n plus 1 distinct values. Okay. And to make that heuristic rigorous, you delve a bit into the descriptive set theory and functional analysis literature and work out what kinds of nice spaces are sufficiently topologically respectable to do this kind of mess on, and you go through that. But the important geometrical point, and this is purely sort of geometry of the space of probability measures on a set, is that the probability measures that satisfy n half-space constraints, n moment inequalities, have support on at most n plus 1 distinct points of the probability space you're working on. And you can convince yourself of this when the probability space is just a finite set, just by drawing pictures on pieces of paper, and all this business about respectable spaces is just enough to make sure that your intuition that works on pen and paper in finite dimensional settings is not a lie in generality. The theorem, which I won't keep up for too long, basically underwrites this heuristic, that if your parameter spaces are nice and respectable, and your admissible set of scenarios for reality takes this form, so you've got some conditions on what reality's response function is, and you've got some pieces of information about this unknown measure, either the whole of the measure or some of the marginals, then you can get away with pretending that the probability measures are in fact discrete. And that's all that theorem says. And just to keep the heuristic up one more time, this means that computing these optimal bounds on the quantity of interest, the lower bound and the upper bound, is just equivalent to solving these finite dimensional problems in which your optimization variables are the positions of those discrete support points, the weights that you've given to them, and in case you don't have a single forward model, what does reality, or what might reality do, what value yi might reality take at the input point xi. And those are your finitely many optimization variables. And all of this got implemented by Mike McKearns principally in an open source way in our Mystic optimization framework, which I'll make a couple of remarks on again at the end. So the classical concentration inequalities or deviation inequalities are just sort of OUQ dressed up, or rather OUQ is an overdressing of these simple basic facts you might have learnt in probability theory. So Chebyshev's inequality, you're just trying to extremize the probability that your random variable exceeds some threshold value given the mean and the variance of that random variable. And one way to prove Chebyshev's inequality would be just to say, okay, I have two mean constraints, which means I get to pretend that my random variable lives on 2 plus 1, 3 points, move those 3 points around, try and make some heavy and others light, keep satisfying these constraints. Eventually you win and you get that upper bound, and that's Chebyshev's inequality all over again. You can do this again with other inequalities, and now I'm in the dangerous position of citing an inequality of someone who's in the room. And so, you know, some people might just call that the bounded differences inequality, but I'd prefer to put a name on it. So what's going on with McDermott's inequality? So this corresponds to this admissible set. It's saying that my response function picks up k independent random variables, assigns the mean of the output at least the value m, but this response function has bounded sensitivity to changes of each of the k inputs individually. So if I change the kth input as much as I like, I cannot change get output values that differ by more than the number dk. And McDermott's inequality just provides an upper bound on the least upper bound of the probability of that output random variable taking negative values in terms of a Gaussian type expression like that. And the reason I put exclamation marks here is that this is a very convenient form, but it's not sharp if I pick any finite k. If I pick a finite k, though, I can actually work out by hand what the least upper bound is. And one of the interesting things that comes out is even in two input variables, you see an interesting expression in one of the cases. What's my worst case upper bound on the probability of, you know, getting to Manchester too late? It depends on the mean time. It depends on the bigger of the two sensitivities. It doesn't depend on the smaller. In other words, the minimum of these two parameter sensitivities, in this sense, carries no information. Not in a sense of having 0 bits of information, but in optimization theory terms, it's a non-binding constraint for this optimization problem. I think I'm going to skip that, except for one thing, just to very quickly summarize. If I add, in addition to the assumptions of McDermott's inequality, the assumption that the response function is actually a linear function, that piece of information is sometimes a bit of binding information. It's sometimes a binding constraint, sometimes not. So even qualitative pieces of information can turn out to have an impact on whether what the extreme value of the optimization problem is, and hence actually carry meaning for you if you're trying to decide whether a system is safe or not. Here's a slightly more real example. This is from the field of seismic safety certification. So here's a truss structure, an electrical tower that this research having been done in California, we're going to hit with an earthquake, a random earthquake, with the ground motion U being drawn from an incompletely specified probability distribution. And the way we've incompletely specified it is we've said what the power spectrum, the expected power spectrum should be, and usually you'd get you'd generate a ground motion with that power spectrum just by filtering white noise through that shape function. Instead, I can say, why don't I consider all probability distributions on, let's say, 200 Fourier modes of this oscillation that have this mean power spectrum. Much broader class. I'm not just sampling from one probability distribution anymore. I'm exploring a broad class consistent with this shape function assumption. So what you get out is not one vulnerability curve for your structure, but an upper one and a lower one. The best possible case and the worst possible case. In the worst case, nature somehow manages to have the right power spectrum but conspires to resonate with your structure at quite a low Richter magnitude and knocks it down. In the best possible case, nature is utterly incompetent and hits all the non-resonant frequencies of your structure, and your structure manages to survive even Richter magnitudes that make almost no physical sense as I understand the Richter scale. It actually stops being meaningful sometime around there. This gap, you want it smaller, you have to make more assumptions. You need to pass to a finer information set than this admittedly coarse one involving just the shape function. And that's where you need expert input from the seismological community. But even in this situation where there's a large region where all you can say about the probability of collapse is it's somewhere between 0 and 1. Turn your head 90 degrees, there's a non-trivial interval estimate of the value at risk. Okay. So you get useful information out of this stuff. I'm going to skip, I think, through most of the other applications I had in mind, but I'll quickly summarize them. So we've spent quite a bit of time analyzing hypervelocity impact. So this is driven somewhat by, say, satellite shielding concerns. There's a lot of very expensive hardware up there in orbit that keeps our mobile phones telling us where we are when we're lost in Cambridge, for example. And if they get hit by a small particle, what tends to happen actually isn't so much that a small micrometeorite destroys the satellite, but hits the outer plate of the satellite, causes the back surface of that plate to then spool off, and it's like a small shotgun blast inside your satellite, and now your delicate electronics have been killed by all this debris. So satellite shielding is an important business, and that's why we got interested in hypervelocity impact. And we studied it under two cases within this optimal UQ framework. One in which you might have legacy data. So you might know your response function at some points in parameter space and never be able to exercise it again. This is, for example, the situation that the Centers for Disease Control are in. They have past data about influenza pandemics. They don't get to start new ones to get more data. Well, we hope that they don't. On the other hand, you might have a great model, and you want to use your model. And you want to use your you might have multiple models. They're good in different regions of parameter space. You quantify how good they are. That defines for you a feasible set around which you can do one of these optimal UQ or generalized Chebyshev analyses. A couple of other applications. Optimal control of magnetically induced hypothermia for the treatment of brain tumors. So very similar to the medical talk earlier, you can design nanoparticles which you can inject into a human, which will preferentially bind to a tumor in the brain that you can't go in and operate on invasively, then you've kind of got this cloud of magnetically susceptible nanoparticles hanging around the tumor that you can excite with an applied magnetic field. They heat up, and it's like giving the tumor a fever. The tumor dies, the rest of the surrounding tissue is okay, you hope. Then the body's immune system comes in and sweeps up the dead tumor tissue in a very clean way, much cleaner than if you had any kind of surgical wound. But can you control it? And can you make sure you don't give an artificial fever to the rest of the brain? Another one we're working on, optimal design of composite materials for low-loss plasmonic applications. So one of the problems with solar cells is they're just too damn big and heavy. And if we could make them out of graphene and a very thin layer of substrate, we could A, have a much lighter thing, and B, the electronic transport properties of graphene are wonderful. So I'm going to skip through that one and just remark a little bit about how you quantify your uncertainty about how good a model might be. For goodness sake, do not say that the uniform distance between your model F and reality is something. Why? Because if your model or reality have a discontinuity or a cliff or something sharp, saying the uniform distance between one function and another is small is saying you've got approximately the right cliffs in exactly the right places. So you're much better off instead using something like, say, a graphical distance. Yes, your feasible set is bigger, but you've got a reasonable chance that you've got approximately the right cliffs in approximately the right places. Yes, your bounds will be looser, your inequality will be worse, but you have a better chance of the assumption you made actually being true. Another point I'd like to mention is that the solutions of these OUQ problems are often not, shall we say, fully dimensional. And the earlier example with McDermott's inequality was a good example. You don't use sort of all of the information or all of the freedom available in the optimization problem when you get to the solution. And the structure of the final solution identifies the key players or the key uncertainties in the problem. Is that me at 5? Okay, good. Okay. So what often happens in the course of one of these optimization problems is you've got, imagine this sort of cloud of points that represents your discrete probability measure evolving around during the course of the calculation. And these support points start to collide, they coalesce, or some of them, maybe they rush off to infinity, but they've got zero mass, so it's okay. Or maybe they stay bounded and they've got zero mass, so that's okay. But the point is you're not seeing the full, you're not using all of the support points by the time you get to the extremizer. And the support points you are using are telling you something very important about the key uncertainties in the problem. But better than that, you can work the cursive dimension backwards. Because once you have this numerical module that we wrote that observes these problems, these degeneracies, these collapses happen, sees them happen, says, oh, well, I don't need that point anymore. I'm throwing it out of the calculation. Now you've reduced the dimension of the problem, so your calculation accelerates. To give you an idea of how much, this is a deliberately over-dimensionalized search over 2-point by 2-point by 2-point probability measures, where I know the extremum is 2 by 1 by 1. So 2 by 1 by 1 is red, that's pretty fast. Green is the original calculation without these clever features. Blue speeds it up a bit. Now I really over-dimensionalize the problem. I search over 4 by 4 by 4 very slowly. That's as fast as I could go, which is starting from sort of cheating, starting with the solution kind of already in hand, or the structure of the solution already in hand. The blue guy starts off being slow, at the dashed lines sees a collapse event, speeds up, and by the end of it, it's going almost as fast as the best it could have done if you knew the solution in advance. A couple of thoughts about future directions. One thing that this kind of viewpoint on uncertainty quantification gives you is the idea of optimally acquiring more knowledge about the system, because you can hypothesize oh, I could run maybe this experiment or this experiment, E1 or E2, and get out these new predictions if I were to get certain answers from the experiment. Well, the trouble is that if I run experiment E1 and happen to get this outcome, my prediction interval is going to be terrible. Whereas no matter what outcome I get from experiment E2, I get a new pretty accurate prediction. So even in the worst case, E2 is a more predictive experiment than E1, so I should run it. And then I should consider my next experiment. Do F1, F2? Well, F2 is sometimes very predictive, but sometimes it's terrible. F1's a better bet overall. So you can imagine using this to plan entire experimental campaigns in an optimal way. And you're sort of like a good chess player, planning multiple moves in advance. Or put another way, you're sort of playing a game against your lack of knowledge about the universe. And a very open question is, just like there are sort of topological games, like the Banach-Mazur game, for which certain spaces are complete if certain players have winning strategies in certain games. Does this UQ game have any fundamental properties? Are there things that you can definitely learn if you have a winning strategy or if you can't have a winning strategy? The other thing I'd like to say is, what if you can make optimal use of random sample data? So compute an optimal statistical estimator for a given situation. So instead of proving a theorem, like establishing the validity of the chi-square test or best linear unbiased estimators or so, work out sort of the schema, the data scheme of your problem, and then compute the optimal statistical estimator for that problem, and then plug in your sample data. So the analogy here would be like what happened with scientific computing after World War II. You had these two camps. What should we use these computers for? We solve PDEs by creating beautiful expansions in terms of Bessel functions and whatever, and then we refer to our nicely computed table of Bessel function values and plug that into our ansatz. But instead, you have the finite element and numerical modeling community come along and say, no, we can take the computers and compute specific to the circumstance on the computer, rather than filling out a special function table and then plugging that into an ansatz. So this would be sort of my vision for the future, that we are on the threshold of being able to optimally compute statistical estimators on a case-by-case basis, rather than having to use one-size-fits-all theorems. So my closing remarks are just by saying that if you pose UQ as an optimization problem, you get natural notions of information content in terms of active or inactive or binding or non-binding constraints. And those give you optimal bounds or optimal relationships between pieces of information. So you really see which assumptions matter, which ones you should care about, which ones you don't need to worry about. Plenty of both theoretical and practical examples. Yes, these problems are still sometimes a bit big, but they're only going to get increasingly tractable. Just like, a century ago, Bayes' theorem was a mathematical truth that you couldn't possibly hope to compute with. Now, we do Bayesian methods all the time. And I think these are interesting times because we may be on the verge of transforming statistical practice, just as was done with PDEs half a century ago. That's some literature on our publications done and forthcoming, and the software that we use, which is all open source. And with that, I thank you for your attention.
Are there any questions?